Competing in the AI transition carries a high capital cost. Alphabet expects its annual capital expenditure to reach $175 to $185 billion by 2026. That outlay sits in direct tension with Alphabet's core business model. As the company deploys AI overviews that answer queries directly on the search page, they risk reducing the outbound clicks that drive traditional search margins. CEO Sundar Pichai is steering the company through this structural margin pressure. Analyzing Google's durability through its consumer applications provides an incomplete picture. The company operates as a vertically integrated stack. This diagram illustrates that technological stack, which divides into three specific layers. At the bottom is the base infrastructure, followed by the algorithmic architecture, and finally the agentic application layer at the top. The consumer products deployed at the application layer are subsidized by the unit economics of the foundational layers beneath them. The entity that achieves the lowest cost of compute per token dictates the pricing power for the AI labor market. At the base infrastructure layer, physical constraints dictate the limits of AI scaling. The focus here is on pod-level deployments of custom silicon. Google's Ironwood TPU v7 links 9,216 chips into a single pod and features high bandwidth memory, or HBM. HBM is a specialized memory architecture that stacks memory chips vertically to enable fast data transfer directly to the processor. This chart compares the capital efficiency of these deployments, starting with a baseline merchant hardware cost. Purchasing an NVIDIA H100 accelerator costs between $5,600 and $7,600 per peak FP8 pflop. An FP8 pflop is a performance metric representing 1 quadrillion 8-bit floating point operations per second. Against that merchant baseline, Google's proprietary Ironwood TPU v7 drops the capital requirement to roughly $2,600 per peak FP8 pflop. While peak processing speed is a common metric, real-world inference economics are often constrained by memory bandwidth. The amount of HBM acquired per dollar invested is frequently the bottleneck for serving large models. This equation breaks down the actual cost of operating these accelerators. The infrastructure cost of goods sold, or COGS, combines the hourly depreciation of the hardware with the hourly cost of electricity. COGS represents the direct costs of producing the compute power. In this calculation, hardware depreciation is the dominant cost term. Google adds to this hardware advantage with facility efficiency, reporting a fleet-wide power usage effectiveness, or PUE, of 1.09. PUE is a ratio measuring how efficiently a computer data center uses energy, with 1.0 representing perfect efficiency, where all power goes to computing equipment. By combining custom silicon pricing with facility efficiency, Google operates with a lower internal cost of goods sold. This allows them to absorb the depreciation costs inherent in the AI transition. Hardware efficiency requires algorithmic efficiency to scale profitably. Under Demis Hassabis, Google DeepMind shifted its research trajectory towards sparse architectures. This network diagram compares a dense neural network to a mixture of experts, or MOE, architecture. MOE is a machine learning technique where only a specialized subset of neural network parameters activates for any given input, and it is the core mechanic in models like Gemini 1.5 and 3.1. By activating only a fraction of the network per prompt, MOE decouples total parameter capacity from the computational cost required to serve a single token. Google exports this research efficiency into the open-weights ecosystem through its Gemma family of models. This scatter plot compares parameter counts on the x-axis against a composite 5 benchmark performance score on the y-axis. Google's Gemma 2 27B model achieves near benchmark parity with Meta's Llama 3 70B. As the x-axis shows, Gemma achieves this output while using 2.6 times fewer total parameters.
The commoditization clock tracks how quickly public models catch up to proprietary systems. Historically, open models trail the closed frontier by approximately 12 months. Google uses Gemma to raise the performance baseline required for competitors to survive. This traps rivals in a low-margin hardware race to serve capable open models, while Google retains the proprietary architecture at the frontier. At the top layer of the stack, the underlying efficiency is monetized at the user surface. Google's current defensive move is to embed AI into existing enterprise workflows. By integrating assistants into Workspace, they justify an expansion in average revenue per user, or ARPU. ARPU is a metric used to measure the revenue generated by one customer over a specific period. But the long-term strategy focuses on asynchronous, autonomous agents that perform active labor substitution. Project Mariner approaches this through browser-based computer use. It relies on decision loops that observe the screen, plan a sequence of tasks, and act on web interfaces independently. Project Jules applies this asynchronously to software production. It operates as a digital junior developer, pulling code from a repository, generating a plan, and submitting pull requests for human review. This move alters the unit of exchange. Vendors stop selling a static software seat license and begin selling raw throughput capacity. This tree map visualization calculates the potential revenue of this labor market. To keep the math grounded, the calculation begins with the total global gross domestic product of $110.98 trillion. Applying global employment constraints, we isolate the roughly 2.38 billion workers in the service sector. Modeling the agent-operable segment assumes that 15 to 40% of those roles feature tasks that are automatable over the next decade. If we apply an enterprise pricing model, a company might pay $5,000 per year for each digital worker equivalent. Multiplying that pricing against the addressable operable seats yields a mid-case revenue potential of approximately $3 trillion annually. Reaching that $3 trillion figure relies on one premise. Google must prove it can safely deploy multi-step autonomous agents in the wild without triggering systemic failures. Pull back to evaluate the entire three-layer stack. Its most significant vulnerabilities are not technical. To function and capture that revenue, agents require distribution across browsers, various operating systems, and enterprise identity surfaces. This level of embedded access places these agents in front of global regulators. Currently, the U.S. Department of Justice is actively pursuing broad antitrust remedies to dismantle Google's existing search and distribution monopolies. Severe privacy liabilities increase as agents shift from answering prompts to retaining cross-device memory and acting on a user's behalf. These systems ingest sensitive context to complete their tasks. This level of autonomy pushes systems into high-risk categories under the EU AI Act, increasing compliance costs and transparency duties. There are also consumer protection risks. Without strict guardrails, third parties could repurpose autonomous agents to scale market manipulation or fraud. Internally, the underlying financial model heavily relies on maintaining a rigid 6-year accounting depreciation schedule for servers and network equipment. If intense competitive pressure forces a sudden 3-year hardware obsolescence cycle, it would strand massive amounts of capital. Cutting the useful life of the hardware in half would reverse Google's cost advantage. While proprietary silicon and architecture fund the defense of the search business today, ultimately, the revenue potential of autonomous agents depends on how Google navigates regulatory friction and the rapid rate of hardware commoditization.